guys. Your one pager is going to look something like this to start with, and then we're going to start with the things that we've been learning the past 2 weeks. So that means the week right now and then the week prior to Thanksgiving, and then we're going to get back to some stuff that has been a minute that we've learned it. So we're going to zoom into this box right here. Okay, and we're going to start with potential energy. And please ignore the gross scab on my hand that y'all can see in the video. All right, someone raise their hand. Tell me, what is potential energy? What's potential energy, Evan?
The potential to do something.
The potential to do something. So that's my stored energy. So PE is stored energy. What affects potential energy the most? What affects it the most, Braden? Height, okay? So it's definitely affected by height. The higher something is, the more potential it has. The lower something is, the lower the potential. What else? What else, Reese? Mass, good. The heavier something is, the more potential it has. The less mass it has, the less potential it has. So guys, to help remember that, because on some of y'all's roller coasters, we didn't label potential energy correctly on the labels. So always remember high point, high potential. Low point, low potential. So high point, that's the highest point, has the highest potential. The lowest point has the lowest potential. So if we're talking about that in terms of a roller coaster, okay, the highest point is going to have that potential, which is usually the first hill. Whatever point is the highest is going to have your highest potential. And then it's always the lowest point, which is usually after the first hill. So just like the roller coaster that we did for our lab, okay, it's the lowest potential is right after that first hill. Some of y'all labeled over here, and that's not your lowest point. This point goes lower than that point. Okay, so when I go from highest potential to lowest potential, I am decreasing. I'm decreasing my potential as I go down. Okay, before break, we also talked about 2 different types of potentials besides gravitational. We talked about elastic and we talked about chemical. Can someone raise their hand and remind me what elastic was? What was elastic, Gabrielle? Good. It was energy stored in something that has like an elastic rubber band. Good. So it could be a spring or a rubber band. Because a rubber band, the further I pull it apart, like my hair tie, okay, the more potential it has. So that's when it's stretched. What about a spring or a clicky pen, Braden? Compressed. Okay, so when it's compressed, it has the most potential. And then what are some examples of chemical potential? Things that have chemicals inside of them, and they have potential, but if you don't use them, they have nothing. Lexi? Batteries, perfect. Okay, They have chemical potential. I can have batteries, but unless I put them in, like the remote, they're not going to do anything for me. Braden? Food, perfect. Okay, I could have these crackers sitting out, but unless I eat them, they're not going to give me any energy. I'm not going to eat them because they're going to go all dry. Yes, Lexi? Fuel. What you got, Grant?
Is there like an outlet that you plug in like a phone charger? Is that chemical?
That's going to be electrical.
Oh,
Yeah.
right, okay.
Okay, one more, guys, that you'll never really think of because y'all don't have anything to do with this, but it's coal. Okay? Coal has the potential. The same thing, and most of y'all probably don't have this, but you can have, like coal, grills or whatever, not electric grills that have like the little black coals. Y'all are like not knowing what I'm talking about, but there's coals and then you can light them on fire. Okay, yeah, thank you. All right, now moving to kinetic. What is kinetic energy? Energy in what? Motion. Okay, what two things affect kinetic energy? What two things affect kinetic energy, Braden? Velocity and mass. Good. So the faster something's going, and I'm going to put speed in parentheses so we just know what velocity is. The more speed, the more velocity, the more kinetic. So if I'm running around, I have a bunch of kinetic, but if I'm walking around, I only have a little bit of kinetic. All right, also the mass. The more mass I have, the more kinetic I have. So if we go back to the bowling balls, if I have a 12-pound bowling ball versus a 6-pound bowling ball, and I throw them at the same speed, the 12-pound bowling ball has more. All right, let's do it in terms of roller coaster. Okay, so I tried to make the same roller coaster I did for potential. Remember, my lowest KE, my lowest kinetic, is usually going to be the opposite of potential. It's going to be at wherever the highest potential is. Remember, they are inverse. So it's going to be where I'm not moving or moving very, very slowly. So I had high potential at the highest point. That means I'm going to have the lowest potential where it's going the slowest. So always opposite. High PE, low, I'm sorry, why did I put PE? I meant KE. Sorry. Okay, wherever I have low potential, I'm going to have high kinetic. So I'm increasing. And I'm going to add something over here that's kind of old, but you need it. Do we remember the phase change graph? When they changed from phases, we had melting right here. And we had evaporating here. Because remember, we're going from a solid to a liquid to a gas. Okay, so remember, as temperature increases, because this is temperature, okay, as temp increases, kinetic energy also increases. And I'm putting stars by that because I know something. All right, next box is going to be mechanical energy. which is just the total. So remember, total mechanical is just 100% of the energy. It's the KE plus the PE, so the total. So I can't have more than 100%. So when someone tells you to give more than 100%, you ain't got it. All right? If PE is 40%, how much is the KE? Yeah, because it should just equal 100. Yeah, that's all about mechanical. It's just the total. Okay, the bottom box is energy transformations. Okay, remember this is when energy transfers from one to another. You have to know what it starts with, what it ends with. Okay, so we're just going to do some examples on the right side here. Okay, power plants, which produce radioactive waste. Okay, power plants. I'm trying to find the color one. They start as nuclear energy. And the point of power plants is to make electricity, so they end at electrical energy. All right, another example is like a lawnmower. Obviously with gas in it. Okay, what do I have to do with the lawnmower first? I have to do what, Braden? Well, before that, what do I have to put in it? Gas, right? Okay, so I have gas. What is gas? Chemical. Okay, good. Do what? No, I'm just saying it's a gas-powered lawnmower. There's electrical-powered lawnmowers that you plug in. We're just talking about gas-powered. Okay? This would be the same as a car, right? Because you have to put gas in the car or fuel in the car to make it work. Okay? What would you have next? Mechanical, okay? Because one, either you could push it or the blades start moving, which actually cuts the grass, which is the point of the lawnmower. So chemical to mechanical. Same thing with a car. You put the fuel in it, then the car starts moving. All right, let's do a blender. What is the first thing I have to do with the blender? I have to do, what? Plug it in, which means it's electrical. Good. Remember, when you plug anything in, it's electrical energy. And then what does the blender start doing? Yes, spinning, chopping food. Okay, which is? Good, mechanical. All right, let's talk about if the energy is wasted between those transformations. Okay, it's not lost. Okay, remember you can't gain or lose because of law of conservation of energy. Energy cannot be created or destroyed. Okay, but it can be wasted. One way it can be wasted is friction. Okay, so if I roll a ball down the hallway, energy is wasted because friction is pulling against it. Thermal energy, so heat energy, can be wasted. And this wasted energy is released into the atmosphere. I spelled that wrong. Well, we've been typing too so much, it's like, Okay, y'all did something like that where wasted energy caused something to not bounce back as much as it was dropped. What were we bouncing? Bouncy ball. So when it's released into the atmosphere, that's what happened with the bouncy ball. That's why when I drop the bouncy ball, it doesn't pop back up to the same spot I dropped it. Energy was wasted and it's released into the atmosphere. So, like a bouncy ball. All right, the next box is heat transfer. Which you can't see. So the first type of heat transfer is conduction. Okay, remember conduction is through solids. What do I have to have for it to be conduction? What do I have to have, Braden? Direct contact, good. Heat through direct contact. So they have to be touching. If they're not touching, you're not using convection for heat transfer. So an example, touching a hot stove. All right, the next one is convection. This happens through liquids and gases. So your examples are the ocean and the atmosphere. Try to spell atmosphere correct this time. Atmosphere. Other examples include the ocean currents, and wind. Which in turn causes weather. Okay, remember the equator is heated up the most. Okay, so the heat rises from the equator to the poles, and then the cool poles, that air sinks back down to the equator. Same thing happens with the oceans. The oceans are warmer near the equator, and they heat up and they rise to the poles, and the poles' cold water sinks back down. Okay, all that is caused by the sun's uneven heating. So draw your little earth. So it starts at the equator and rises to the poles. So warm air rises. Why does it rise? Because it is what? What's its density? Less. Okay, warm air rises because it is less dense. Cool air sinks because it is more dense. Okay, and for convection to happen, you have to have different temperatures. If everything is the same temperature, you're not going to have convection. You have to have something that's hot, something that's cold. Okay, last heat transfer, y'all. Which is radiation. What's the best example of radiation? The sun. Heat from the sun. Okay, remember, this can happen through solids, liquids, gases, and empty space.